What's up, everybody? This is Erin from ErinsAudioCorner.com, and today I'm going to review a drive unit, and it is made by Audio Development. It is called the W800NEO. And this is it. It is an 8-inch mid-bass. It's just over about 2-inch mounting depth. You can see it. Now, the thing that I find really interesting, it's got banana plug ports on the bottom of it. I don't really understand why. I don't know why manufacturers make shallow mount woofers and then stack these big old ridiculous terminals on them. Why don't they just give us something we can solder onto or something like that? I don't know. My suggestion, if you're going to use this in a shallow mount enclosure and you're really tight for space, is just take these banana terminal things off and, you know, just put like a little quick slide down there on the bottom. But that's a pretty minor gripe. I'm not going to get into subjective thoughts because when I test raw woofers, I do this in a couple of different ways. Number one is I use my clippable distortion analyzer, and I will measure the linear excursion and the fill small parameters. And then once I'm done with that, I'll take it into my garage and I attach it to my partition wall between my one portion of my garage and the other portion of my garage. And I do that in order to get the frequency response. So there's really no accurate way to subjectively test a raw drive unit. I mean, you would want to implement it into part of a speaker or part of a system of a speaker or something like that. So I'm not going to get into my subjective thoughts on how it sounds because to me it's just all superfluous and it would be kind of silly to do something like that with a raw drive unit. Therefore, I'm going to jump straight into the actual raw data, discuss to you what the measurements look like and what their importance are in areas that I find that may be troubling or positives about it, and then kind of wrap it all up, give you a general takeaway from my perspective and let you decide if you want to buy it, if it fits your needs or not. So let's do that. So I'm at my website, which again is ErinsAudioCorner.com, and if you go to home right now, you can see where this is, but generally this speaker will be found in the drive unit section. It's at the top because it's my most recent. And these are some pictures that I've taken. And we'll scroll toward the bottom here. So this is the manufacturer's spec sheet right here. And here is the mounting depth, 56 millimeters mounting depth, which is just over 2 inches or so. And here are some of the specs that they provide. They say a frequency response range of 40 hertz to 2 kilohertz, maximum power input about 100 watts. dB/SPL is 90 dB. I don't know if they're ranking that at 2.83 volt input or not, but whatever. And 19 millimeter X max, which when you're looking at the speaker, you know, just from looking at it, it's probably not going to have almost a full inch of excursion one way. So you got to take that 19 millimeter X max as most likely what they mean that to be is two-way, peak to peak excursion. So let's keep going. This is my bit about where I tell you, hey, this is why I don't get a subjective analysis. And moving on, I test this, like I said before, with Clipple's distortion analyzer. I use a laser and I use their Pro driver stand. I've linked all of that here. These are the till small parameters that I've gathered from that test. And you can see a QTS of about 0.474. which not necessarily is great for infinite baffle configuration or door configurations, but it's not so low that you would expect the suspension to flop around. So it's reasonable for an infinite baffle configuration. And the sensitivity measure for the TS parameters is about 93 dB, but I generally don't use the TS parameter sensitivity. I will actually use the frequency response to figure out what the sensitivity is over a particular range. Using Clipple's distortion analyzer and their large signal identification module, I measured the linear excursion, and the linear excursion for Clipple is defined as a point, at least for mid-woofers, where the distortion exceeds the point of 10% total harmonic distortion in all. And they break that down in components of motor force, suspension, and inductance. And in this case, this woofer's maximum linear excursion is capped at about 4.9 millimeters. So I'm just going to round it and say 5 millimeters. And we'll get into why that is. So This is a graphic of the motor force, and you can see that at rest it's about 3.4, and then as the woofer makes excursion and goes out of the coil either forward or backwards, the motor force decreases over excursion. And then this is the stiffness of suspension, so this is how tight the suspension is getting as the woofer is moving forward or backwards. And this is the inductance change with excursion, and in this graphic I can see that they are using a shorting ring to help lower distortion. Now inductance is important as you play a speaker near its FS. The lower you play the speaker, the closer to the FS you play the speaker, the lower that you want the inductance to be, the more symmetrical you want the inductance to be. That will help keep distortion down. And in this case their shorting ring looks like it's about 5 to 6 millimeters too far inset of the voice coil. So by shifting that, they could actually increase the inductance number that I provided in the table earlier. And we're going to keep going. This is a intro to what inductance means. Now this is the FS shift. Now this is something that I'm going to provide in all my data because I think it's important for people to understand that a speaker's FS does change with excursion. A good speaker won't exhibit a large change in FS with excursion. And in this case, you know, I'm seeing ballparking about 5 or so hertz of change with excursion over about 12 millimeters of actual mechanical excursion. So that's not terrible. If I actually go the other way though, it's closer to, what is that, almost 10 or so, just kind of ballparking this. So the FS does change with excursion. Same thing, QTS, as you move the speaker forward or backwards, the suspension gets tighter and the QTS actually just changes as you move the speaker forward or backward. This is one area where it's important to understand that using the static modeling parameters that we most often use can be misleading, and that's why I also provide this table, which the main takeaway that you want is this sentence right here. If you're accurate system modeling, large plus cold parameters are preferable to small signal parameters because they more closely reflect the parameters and their typical operating range. This is the column that I'm speaking of. So if you were to go and model the speaker, this is the column that you would want to use because it shows the more accurate parameters as a speaker is actually being used. And you can see that if you compare to small signal, some of these values are changing. So let's mainly go look at QTS. So 0.44 QTS in static state, just a very small voltage, but when you apply a little bit more voltage, it shifts down a little bit. Same thing we saw FS here, same thing you saw in the graphics earlier. So that's just an interesting note to take home. Frequency response is important. Now on this speaker, I measured the average, I'm gonna blow this up a little bit, I measured the average frequency response output in SPL to be about 89.6 dB. So that's from 300 hertz to 3 kilohertz. If you bring that down to a range where you're most likely going to be using this, which is a mid bass, so about 80 to 500 hertz, you're closer to 90 to 91 dB output. So this is actually a pretty high sensitivity mid bass when you're looking at it in that context. This dip around 90 hertz concerns me. It also shows up as a blip in the impedance curve. And then as you get higher to about, I'm going to say once you start exceeding 500 hertz, you start to get a roll off and you see a little blip in impedance there. And this is the on and off axis frequency response. What this means is, let's say that you're listening to the speaker on axis. That means you are pointed directly at the speaker. As you move around the speaker or as the speaker moves around you, so let's say it's going this way, that would be about from you maybe 10 degrees or so off axis, then maybe 30 degrees, 45, and then the further it gets around to you all the way to the side, which maybe be like this, would be 90 degrees. It's important to know what the speaker is doing as you move off axis because it will show areas of resonance, things that are important like that. And in general, it just gives you a very good idea of the limitations of the speaker's range when you're trying to use it. If you were trying to play this as a mid-range or a mid-woofer and play it up as a two-way to meet like a, let's say a 2-inch or a 1-inch dome tweeter, normally you would try to cross that around 2 to 3 kilohertz, and as you can see there's a big gap in output at the 2 kilohertz region. That's about 84 dB at 60 degrees off axis versus 0 degrees on axis is about 92. So 92 minus 84 is 8. So you're about 8 dB down in output at 60 degrees off axis. But if you follow it back up and then go and look closer between the 500 to 1 kilohertz region, you can see that all of these measurements align pretty much the same. So that tells you that you're good within this region to cross over. And again, if you're using this as a dedicated mid-bass, you're probably going to be crossing closer to the maybe 300 to 500 hertz region. I wouldn't go any higher than 500, 600 hertz or so, give or take. But most people aren't going to be using it that high anyway. And on the low end, I would also say, again, the 80 hertz region, 60 hertz region, somewhere around there. Typical 8-inch mid-bass crossover point is reasonable for this speaker. This is the normalized response. So this is basically just on-axis response minus the off-axis response, and it shows you a baseline comparison in that regard. This is my distortion measurements, and I'm going to go to the zoom version. There is a peaking of distortion at full output, which in my case was 12 volts, so about 103 dB on average at 1 kilohertz, and it reaches over 2% THD. Below that, at more typical range, you're looking in between, let's say 200 to 500 mid-range, you're within about 1%, and below 200, you're creeping up to as much as 5% at full tilt. But when you implement a high-pass filter of like 60 hertz or 80 hertz, somewhere around there, this distortion will come down a good bit, and it'll be more tolerable. Now this is compression. Compression just means that if you turn the volume up 3 dB, you expect the output to increase by 3 dB. Anywhere that you see a negative value in my graphic for compression means that you're losing output. So for example, let's look at this 80 hertz region. And the 12 volt, which is the red, the 12 volt mean SPL is 103 dB. Now that's calculated, so that's theoretical. According to this graphic, if I were trying to play it at 103 dB, I would lose almost 2 dB to compression, which means that I would actually be 103 minus 2 would be 101 dB output. So there's significant compression around the 80 hertz region, and then when you go higher up in frequency, there's some more compression, but that's not terrible. Again, using a crossover, a high pass filter, is going to limit the compression because you're going to limit the power that's being sent to the speaker at around the 60 to 80 hertz region. So that'll help out in the compression area. This test is maximum long-term SPL testing. I do this per an IEC standard, and this is helpful to understand the maximum output that you can achieve based on threshold of compression or distortion, which are all described and set in this discussion here. And I'm going to blow through this because I think if you want to go back and read it, you can. But the point is, I test this two different ways. One is 20 hertz to 20 kilohertz, and the other is a limited range. And in this case, I chose 80 hertz to 5 kilohertz just to say if I was going to play it as a mid-bass up into maybe the higher regions where most people are probably not going to play it anyway, but this gives me something to compare to against future speakers, then I'll know what that SPL limitation there is. So for 20 to 20, the maximum output is 103 dB at 1 meter. For 80 to 5 kilohertz, it's 108 dB at 1 meter. So that's actually a really high output speaker, and that's largely due in part to its already high sensitivity of about 90 to 91 dB in that mid-bass region. So this being a high sensitivity speaker is very, very helpful. This is my bottom line, so I'm going to wrap this all up. Looking at this, I'm saying the linear excursion is limited to 5 millimeters one way. So one way. So the maximum output that you can get from this speaker on the low end without exceeding a 10% THD distortion threshold is 5 millimeters. Now, mechanically speaking, this speaker goes to about 10 millimeters one way, and I was able to sit here and observe that. I saw that in the data, and I also was able to tell by just watching the speaker and listening for when it would, hit mechanical limits. So 10 millimeters one way mechanical, 5 millimeters one way linear. That's important to note. Let's see, there's some suggestions on how the linear excursion could be improved. You guys probably don't care about that. That's more for engineering purposes. Sensitivity average from 300 to 3 kilohertz is almost 90 dB. For the mid-bass region, you're talking about 90 to 91 dB. If you were to model this speaker for a sealed enclosure, I got 2.25 cubic feet for a QTC of 0.707. If you wanted to use this IB in a door or something like that, then that would be represented by this red line, and that would show you, a comparison between a sealed enclosure versus IB type. So that's just for people who are interested in that. Distortion and compression we've already talked about. Bottom line here, use this as a mid-bass driver based on the data I'm seeing, and depending on the output levels that you want to achieve, you're probably looking at a 60 to 80 hertz high pass filter on the lower end. And I wouldn't push this higher than 500 hertz on the higher end, just because there are some weird things that once you get above 700 hertz or so that kind of stand out. And if you cross this maybe to 400 hertz, I think that'll be great. The fact that they do use a shorting ring is nice. That'll help limit the distortion on the upper end of that crossover area. So if you wanted to push this to the 400 or 500 hertz region, you should be able to without any real audible distortion. But I would still limit that to 300 or 400 hertz just to stay on the safe side. Obviously, your mileage may vary. These are just suggestions based on what I'm seeing in the data. And that's it. Hope that you learned something, and I'm going to end this now.